Now, when we orient the crystal with the axis parallel to the easy axis of antiferromagnetic alignment parallel to the applied magnetic field, and we apply a very, very low magnetic field, we get this. So this is magnetization. We measure magnetization, something that is crazy. In an antiferromagnet, who cares for the magnetization? We know it's zero. You remember? In a crystal. We are not using neutrons. But we were crazy enough, probably we drink something before going to the experiment, that we decided to measure magnetization. Magnetization, of course, is zero in the paramagnetic region. But then, suddenly, at the ordinary temperature, we start having an increase, like in a ferromagnet. This is one dilution. This is another one. Now, to understand this, these are different applied magnetic fields. 0.01 oester. This is very low. We had to screen the Earth magnetic field to apply this magnetic field. Here is 0.3, and this is 4 oester. Okay, this corresponds to the 4 oester curve. And this value, because we plot all together, this value is in fact the susceptibility times this little magnetic field. Okay? So that tells you that this value of the magnetization is very low. We are measuring something really very low, very small, very small. Here I have a dilution of 51%. I told you that in one case it will be very high. It's in the manganese fluoride. Okay? We need 51% of zinc substituting manganese to have this huge effect. Well, huge, small effect, sorry. But with 25%, the effect is, you see, 6 times smaller. So we see the effect of KH much bigger. No problem. We can make another experiment. Let's see how much is the susceptibility of the antiferromagnet. Once we know K, we can correct all these curves by the effect of KH. Because you follow me, okay? That we are measuring magnetization that is some kind of let's make a question. Something surprising plus another term, K parallel times H. This is the induced magnetization by the magnetic field. So we are measuring both. What we want to know is how much is this. So let's see how much is K parallel and calculate how much this term is in order to correct the data. So that's what we did. And here are the data corrected. We call MR, which is this one, we call it MR. So we move the other part is M minus. So here is, sorry, MR, M minus K parallel times H. And then we get these curves. And of course, magnetization is zero above TC. Same for the 51%, then for the 25%. But now we can take the value at an arbitrary temperature. So let's put the value at 5 Kelvin, for example. The magnetization value, MR, sorry, not magnetization, but this anomalous magnetization the value for each curve at, say, 5 Kelvin, and normalize the curves according to this value. When we do that, of course, all that collapse in a single curve. What that means? That means that depend by a scale factor from the magnetic field. So the magnetic field, this is a small, very small magnetic field, only affects in a scale factor. Okay? And you can ask why you didn't measure above 4 Oester. Because we did, but there was nothing happened. I mean, it was saturated, the phenomena saturated at 4 Oester, at very low magnetic fields. But this is a disturbance of the substitutional defects we have produced in the antiferromagnetic lattice. Now we have two crystals, one 51% of substitution, the other one 21% of substitution, and both have the same phenomena. And next question is it different or is not? Can we collapse both data sets in one unique set of data? To do that, because if we substitute many atoms of manganese, the ordering temperature will decrease. So to do that, we have to normalize the temperature, the ordering temperature. So when we normalize, sorry, this is 51, sorry, that was 51 and was the same for 25%. Now, when we normalize the temperature, we get this. All the data sets for the manganese fluoride, wherever the dilution is, collapse into a single curve. That indicates that the amount of substitution only introduces a scale factor to the phenomena. Okay? So it's something intrinsic of the dilution effects, and not the how many diluted sites were, and which is the applied field we use to measure the effect. Okay? So this is the phenomenon. It's intrinsic to what we have made bothering, perturbating the antiferromagnetic lattice. Well, our next question was is this a phenomena that only depends on manganese fluoride? Can we look for another case? So we went to another antiferromagnet. This one is another isotropic ferromagnet. We tried to keep on to modify the minimum. We knew that manganese fluoride was very isotropic, so let's look for another isotropic one. Of course, you tell me, well, is that true? And I would say, no, it was not true. We went to iron fluoride, but iron fluoride is very anisotropic. And since the very beginning, the first measurement we did showed that the problem was completely different. Totally different. So we thought, okay, we have changed too many things. Let us keep on the same Heisenberg model, okay? Low anisotropy system. And we look for that. This is a low anisotropy antiferromagnet. There is a big series of compounds, and so we could choose here also. There is ammonia and cesium and more. I will give you only examples of potassium and rubidium derivatives. And we can also substitute the iron by indium. Indium is non-magnetic, so we can substitute the magnetic sites in the antiferromagnetic lattice by non-magnetic impurities.